Hi everyone, welcome to the Sleep and Learn channel. Tonight, we invite you to relax and explore the most interesting and calming facts about quantum physics, a world where reality becomes soft, mysterious, and full of quiet possibilities. Find a comfortable position, slow down, and let your mind gently drift as we uncover the hidden beauty of the universe at its smallest scale. Part 1. The gentle birth of the quantum world. At the dawn of the 20th century, physics encountered a quiet mystery. Classical theories, which had so elegantly described the motion of planets and the fall of apples, began to falter when scientists examined the smallest scales of nature. The study of quantum physics emerged not from dramatic explosions of knowledge, but from subtle inconsistencies, soft whispers in laboratory data that suggested reality was more delicate and intricate than previously imagined. One of the earliest clues came from the study of light. For centuries, light had been described as a wave, spreading smoothly across space. Yet experiments on heated objects revealed something puzzling. The energy emitted did not vary continuously, but in tiny, discrete packets. In 1900, Max Planck proposed that energy is exchanged in small units called quanta. This simple mathematical assumption, made to solve a technical problem, quietly opened a doorway into a new understanding of nature. Soon after, Albert Einstein suggested that light itself could behave as if it were made of particles, later called photons. This idea explained the photoelectric effect, where light striking metal can gently release electrons. For this insight, Einstein would later receive the Nobel Prize, not for relativity, but for helping to establish the quantum nature of light. What makes quantum physics so calming to contemplate is its reminder that certainty dissolves at small scales. The world of atoms and electrons does not follow rigid mechanical paths. Instead, it unfolds as a tapestry of probabilities. Rather than asking where exactly is a particle, quantum theory invites us to ask, where is it most likely to be found? In this way, the universe at its smallest scale resembles a soft cloud of possibilities. In 1926, Erwin Schrödinger introduced a wave equation that described how these probability clouds evolve over time. The equation does not describe solid objects moving like tiny billiard balls. Instead, it describes wave-like patterns of potential, mathematical ripples that determine how particles may appear when observed. Equally influential was Werner Heisenberg, who formulated the uncertainty principle. This principle states that certain pairs of properties, such as position and momentum, cannot both be known with perfect precision. The more accurately one is measured, the less precisely the other can be determined. Far from being a limitation of technology, this uncertainty is woven into the fabric of reality itself. There is something quietly poetic about this discovery. At its deepest level, the universe resists absolute certainty. Precision gives way to balance. Knowledge comes with gentle trade-offs. The quantum world teaches that nature is not rigidly fixed, but subtly fluid. As we begin our exploration of quantum physics, it is helpful to set aside classical expectations. The smallest particles do not behave like miniature versions of everyday objects. Instead, they exist in a realm where waves and particles merge, where measurement shapes outcomes, and where probability replaces determinism. Wave-particle duality and the double-slit experiment. One of the most elegant and calming ideas in quantum physics is wave-particle duality, the realization that light and matter do not fit neatly into classical categories. In everyday life, objects are either particles, like grains of sand, or waves, like ripples on water. Yet at microscopic scales, nature behaves in a way that gently blends these two descriptions. The story begins with experiments on light. For centuries, light had been understood as a wave, especially after the work of Thomas Young, who demonstrated interference patterns using two narrow slits. When light passes through two openings, it does not simply form two bright regions. Instead, it creates a series of alternating light and dark bands, a pattern characteristic of waves overlapping and reinforcing or cancelling one another. This peaceful pattern of light and shadow is known as an interference pattern. It resembles the gentle crossing ripples that appear when two stones are dropped into a still pond. Where crests meet crests, brightness appears. Where crests meet troughs, darkness forms. The experiment suggested that light spreads like a wave across space. However, the early 20th century introduced a quiet surprise. Experiments showed that light sometimes behaves as if it arrives in localized packets of energy. This dual behavior seemed contradictory. How could something act like both a continuous wave and a localized entity? The mystery deepened when scientists performed the same double-slit experiment not only with light, but with electrons, tiny components of atoms traditionally thought of as matter. Remarkably, electrons also produced interference patterns. Even when sent one at a time toward the slits, the overall pattern that gradually formed on a detection screen displayed wave-like behavior. The experiment reveals something profoundly subtle. Each individual event appears discrete, a single mark on a screen, yet the distribution of many such events forms a wave-like structure. It is as if nature keeps its options open until the moment of measurement, gently unfolding probabilities into specific outcomes. What makes the double-slit experiment especially fascinating is the role of observation. When detectors are placed at the slits to determine which path an electron takes, the interference pattern disappears. The system behaves differently depending on whether or not path information is measured. This does not imply that consciousness creates reality, but rather that measurement itself is an interaction that changes the system being studied. The mathematical description of this behavior is provided by the wave function, a central concept in quantum theory. The wave function encodes all possible outcomes and their probabilities. It evolves smoothly according to Schrödinger's equation, yet when measured, it appears to collapse into a single observed result. This transition from possibility to actuality remains one of the most gently debated mysteries in physics. Wave-particle duality teaches us that nature is not limited by the categories we create. The quantum world does not insist on being either wave or particle. Instead, it reveals that these are complementary descriptions, different perspectives on the same underlying reality. In contemplating this idea, there is a quiet beauty. The universe at its smallest scales is neither rigid nor chaotic, but subtly balanced between forms. It reminds us that reality can be richer than our expectations, layered, fluid, and quietly profound. Quantum superposition and the quiet mystery of possibility. One of the most intriguing and calming principles in quantum physics is quantum superposition, the idea that a system can exist in multiple possible states at the same time. Unlike objects in everyday life, which appear to occupy one definite condition, quantum systems are described by combinations of possibilities until a measurement is made. To understand superposition, it is helpful to think of musical harmony. A single piano key produces one note, clear and distinct. But when several keys are pressed together, the sound becomes a chord, multiple tones existing simultaneously. In a similar way, the quantum state of a system can be a chord of different possibilities blended together mathematically. This idea is not merely philosophical. It arises directly from the mathematics of quantum theory. The wave function, introduced by Erwin Schrödinger, allows multiple states to be added together. These combined states evolve smoothly over time, forming interference patterns not only in space, but in probability itself. A famous thought experiment illustrates the strangeness of superposition. In 1935, Schrödinger proposed a hypothetical scenario involving a cat placed in a sealed box with a mechanism triggered by a quantum event. According to the mathematical description, before the box is opened, the system can be described as a combination of cat alive and cat not alive. The thought experiment was not intended to suggest that cats truly exist in such conditions, but rather to highlight the contrast between quantum theory and everyday intuition. What makes superposition especially fascinating is that it is experimentally observable in microscopic systems. Carefully designed experiments demonstrate that quantum states can remain in blended configurations, producing measurable interference effects. Only when the system interacts strongly with its environment does it appear to settle into a definite outcome. This transition from superposition to a single observed state is closely related to a process called decoherence. Decoherence occurs when a quantum system becomes entangled with its surroundings, causing the delicate balance of possibilities to disperse into the environment. In this way, the classical world of definite outcomes emerges gradually from the quantum world of layered potential. Superposition gently reshapes our understanding of certainty. Rather than imagining nature as choosing a single path from the beginning, quantum theory suggests that multiple paths may coexist mathematically until interaction selects one. The universe, at its smallest scales, appears to hold many possibilities in quiet balance. There is something deeply peaceful about this idea. Superposition does not imply chaos. Instead, it reflects structure at a deeper level. The mathematics governing these blended states is precise and orderly. The seeming strangeness arises not from disorder, but from richness, from a reality that is broader than everyday perception. In recent decades, superposition has moved beyond theory into practical application. Technologies such as quantum computing rely on systems that can maintain superpositions of states, allowing calculations to explore many possibilities simultaneously. Though still in development, these devices demonstrate that superposition is not merely an abstract concept, but a physical resource. Contemplating superposition invites us to see the world as layered and subtle. Beneath the stable appearance of objects lies a quieter realm where alternatives coexist, where probability flows like overlapping melodies, and where observation gently guides possibility into form. Quantum entanglement and the subtle nature of connection. Among the most fascinating and quietly profound features of quantum physics is quantum entanglement, a phenomenon in which two systems become linked in such a way that their properties are correlated, even when separated by great distances. Entanglement challenges classical assumptions about independence and locality, yet it does so with mathematical precision and experimental confirmation. The concept first emerged during the development of quantum theory in the early 20th century. In 1935, Albert Einstein, along with colleagues Boris Podolsky and Nathan Rosen, published a paper questioning whether quantum mechanics provided a complete description of reality. They described a situation in which two systems interact and then separate, yet remain correlated. Einstein famously referred to this as spooky action at a distance, expressing discomfort with the idea that measurement of one system could instantly determine the state of another far away. At first glance, entanglement seems to suggest faster-than-light communication. However, careful analysis shows that while the correlations appear instantly, no usable information travels between the systems in violation of relativity. The phenomenon reflects deep statistical relationships rather than classical signals. In this sense, entanglement preserves the structure of modern physics while expanding our understanding of connection. The debate over entanglement continued for decades until a major theoretical breakthrough came from John Bell. In 1964, Bell derived inequalities that provided a way to experimentally test whether quantum correlations could be explained by hidden classical variables. His work transformed philosophical discussion into measurable science. Beginning in the 1970s and 1980s, experiments, notably those led by Alain Aspect, demonstrated violations of Bell's inequalities, supporting the predictions of quantum mechanics. These experiments showed that entangled systems exhibit correlations stronger than any classical theory can account for. What once seemed abstract became an established feature of physical reality. There is something deeply calming about the idea that separation does not always imply independence. Entanglement suggests that once systems have interacted, their descriptions may remain intertwined. The mathematics does not describe isolated fragments, but unified states extending across space. Importantly, entanglement does not imply mystical influence or conscious control. It arises naturally from the structure of the wave function describing combined systems. When two systems are entangled, they no longer possess independent states. Instead, only the state of the whole can be fully specified. In recent decades, entanglement has become a practical resource. It forms the foundation of quantum cryptography, which allows secure communication by detecting any attempt at interception. It also plays a central role in quantum computing, enabling correlations that classical systems cannot replicate. Researchers have even demonstrated entanglement over increasing distances, including between ground stations and orbiting satellites. These achievements illustrate that entanglement is not fragile theory but measurable phenomenon. Contemplating entanglement invites a shift in perspective. The classical worldview often emphasizes separateness, distinct objects occupying independent positions in space. Quantum physics, however, reveals that relationships may be more fundamental than individual components. In the quantum description, connection is not secondary. It is built into the structure of reality. As we move forward, we will explore how these principles shape emerging technologies and deepen our understanding of the universe at both the smallest and the largest scales. Quantum tunneling and the subtle passage through barriers. One of the most quietly astonishing features of quantum physics is quantum tunneling, the ability of a system to pass through a barrier that, according to classical physics, should be impossible to cross. In everyday experience, a ball thrown at a solid wall either rebounds or stops. In the quantum world, however, the description is more subtle. Under certain conditions, there is a measurable probability that the system will appear on the other side of the barrier. This phenomenon arises naturally from the mathematics of the wave function. In classical mechanics, energy determines strict boundaries. If a system lacks sufficient energy, motion beyond a barrier is forbidden. Quantum theory, however, describes systems as waves of probability. When these probability waves encounter a barrier, they do not abruptly end. Instead, they diminish gradually within it. If the barrier is thin enough, the wave may extend beyond, allowing a small but real likelihood of transmission. The effect was first explored theoretically in the early 20th century as physicists sought to understand radioactive decay. In 1928, George Gamow used quantum tunneling to explain how alpha particles escape atomic nuclei. Classically, these particles lacked sufficient energy to overcome the nuclear barrier. Yet tunneling provided a clear explanation. The wave-like description allowed a finite probability of escape. Quantum tunneling is not rare or exotic. It plays a vital role in nature. It is essential to the process of nuclear fusion within stars. In the core of the Sun, atomic nuclei approach one another despite strong electrostatic repulsion. Tunneling enables them to overcome this barrier, allowing fusion reactions to occur at temperatures lower than classical estimates would predict. Without tunneling, the steady light of stars would not exist in its present form. On a smaller scale, tunneling also underlies modern technology. Devices known as scanning tunneling microscopes rely on this effect to image surfaces at atomic resolution. By measuring tiny tunneling currents between a sharp metallic tip and a conductive surface, researchers can map structures with extraordinary precision. What once seemed paradoxical has become a powerful scientific tool. The probability of tunneling depends delicately on the width and height of the barrier. Thicker or taller barriers reduce the likelihood dramatically. This sensitivity reflects the exponential behavior of the wave function inside the barrier, a gradual fading rather than a sharp boundary. There is something surprisingly calming in this idea. Boundaries in the quantum world are not absolute walls but regions of reduced probability. The universe does not divide itself into strict impossibilities. Instead, it assigns degrees of likelihood. Even when an outcome appears classically forbidden, quantum theory allows a quiet chance. Importantly, tunneling does not violate conservation of energy. The system does not gain extra energy to cross the barrier. Rather, the probabilistic nature of its description means that the classical picture of a definite trajectory does not fully apply. The wave function provides a broader framework in which transmission becomes mathematically consistent. In chemistry, tunneling influences reaction rates, especially for light atoms such as hydrogen. Certain reactions proceed faster than classical models predict because particles effectively pass through energy barriers rather than climbing over them. Thus, tunneling subtly shapes molecular processes and biological systems. Contemplating quantum tunneling invites a shift in how we imagine obstacles. At the smallest scales, barriers are not rigid partitions but gradients in probability. What appears impenetrable from a classical viewpoint becomes, in the quantum description, a region where likelihood gently decreases and then rises again.